Hi, I'm Sam, a graduate student at the University of Michigan in Ann Arbor, and I'm presenting our submission to the 2015 TI Innovation Challenge, PowerBlade. PowerBlade is made to measure the power consumed by an individual device. Our system is so thin, you literally plug through it and then into the outlet. This allows PowerBlade to inconspicuously sit between the plug and the outlet, measuring power in real time and transmitting that data over Bluetooth Low Energy to nearby smartphones.
Let's talk about why we are interested in the problem of power metering. Here's a story about a professor we know. This professor owns a house in Ann Arbor, and like any good Ann Arborite, he wants to conserve energy. Once a month, his electric company sends him a billing statement showing him how he ranks against his neighbors. He is astonished to see he uses more power than 98% of his neighbors. This is no good at all. He wants to make his house green, but how? What is using all the power? Is it the AC? Maybe the fridge? Or is it just a bunch of things adding up? The data from his monthly power bill is just not enough. In order to actually answer the question, he needs to measure the power use at each outlet. And he's not alone. While we all agree that conserving energy and saving money on electricity bills is good, the average consumer lacks the tools and knowledge to actually reduce his or her power consumption. Existing power meters, such as the watts up and the kilowatt, are simply too large and too expensive to deploy throughout a household. They also don't have wireless connections, so data can't be streamed directly to a computer. In order to overcome these problems, we designed our own system, PowerBlade. In quantities of 10,000, PowerBlade could be produced for only $10 apiece, and yet is still just as accurate as previous meters, with an average error of less than 5%.
In order to make our meter as small as possible, we had to revisit many of the choices made by other systems. The first of these is the power supply. Traditional AC to DC power supplies require too much volume for a plug-through power meter like PowerBlade. Using a simpler, right-out-of-the-textbook design allows us to reduce the size of the supply considerably if we can reduce the power draw of the rest of the system. The half-wave circuit shown requires only 4 components to function. On the positive half-wave, Cout is charged to the voltage rating of the Zener diode, about 9 volts. On the negative half-wave, the load is powered from the charge in Cout, and the AC shunts over Zin. This retro power supply design takes up very small volume, but only supplies up to 1 milliamp continuously. This output is fed into a TI TPS 62122 3.3 volt regulator to generate our system rail. The 62122 was selected for its high efficiency even at such low currents. For our onboard processing, we used the TI MSP430 FR5738. Its extremely low current requirements and 16 kilobytes of integrated FRAM provide a high-function MCU without requiring significant power or volume resources. In order to calculate power, the MSP430 must be able to sample both current and voltage waveforms continuously in real time. This is important because complicated capacitive and inductive loads, aka non-unity power factor loads like the one shown, have distorted current waveforms that lead or lag the voltage. This plug-through form factor requires a novel contact method. We utilize 2 flexible gold tabs built into the PCB itself. To measure voltage, we simply pass the AC phase line through a resistive divider and read it on an ADC on the MSP430. Sensing current is more difficult. We can't break the path to measure current like a multimeter does. Instead, we go back to the physics textbook. As current flows through the cable, it generates a magnetic field that circles the wire. Placing an inductor perpendicular to the field causes the magnetic flux to pass through its coils, being converted to voltage. In essence, we use the inductor as a magnetometer. This signal is almost unusably small. Only a TI OPA 333 operational amplifier with a 10 microvolt offset can discern signal from noise within our power budget. This signal is further amplified before being read by the MSP430. With the exception of the 333, all amplifiers used in our design are TI OPA 369s, selected for their extremely low current requirements of 700 to 800 nanoamps per channel. Finally, the data from the MSP430 must be transmitted to the user. For this, we selected Bluetooth Low Energy, thus enabling smartphones to receive the data using a custom app. The BLE radio itself draws significant power relative to the rest of the system, but is still capable of sending data updates about once per second. Now that you know how it works, let's see PowerBlade in action. The BLE data from PowerBlade can be displayed in our custom smartphone application. When the load is enabled, the app displays true power at the top. Other useful information in the app include RMS line voltage, apparent power, and the cumulative energy consumed by the device. All of our hardware and software is open source. Check it out at github.com/lab11/PowerBlade.